Look at the Dubai skyline on any given afternoon, and the Burj Khalifa appears completely frozen against the horizon. But that apparent stillness is an illusion. Under extreme conditions, the summit of this 828-meter titan is designed to sway by up to 1.5 meters. That distance alone sounds terrifying to anyone standing near the top, but structural engineers don't fear a tower that simply bends and returns to its center. Skyscrapers are supposed to deform. The real nightmare begins when the wind stops acting like random, chaotic weather and starts pushing in an organized, repetitive pattern. The terrifying question driving this investigation isn't just how far the Burj Khalifa can bend. It's what happens if the atmosphere learns how to lock into the building's own internal rhythm. Because if the wind successfully syncs with a structure this massive, it doesn't just make the building sway. It progressively tears the massive steel and concrete connections apart from the inside. Every super-tall structure possesses a natural dynamic rhythm of its own. So, what happens when the wind learns how to keep time? To understand why movement could theoretically destroy a super-tall building, we first have to discard the most common assumption about how wind works. We tend to imagine wind as a giant and invisible hand pushing continuously against a surface. If that were true, the primary threat to Burj Khalifa would just be the maximum velocity of a single storm. If the wind blew hard enough, the building would lean back. And if that continuous push exceeded the ultimate structural capacity, the materials would simply fail. But that is not how fluid dynamics interact with an 828-meter obstruction. Amplitude alone does not define the danger. Timing matters just as much. Think of a heavy playground swing. If you walk up to that swing and deliver one badly timed and hard push, the swing might jolt forward, but it will quickly lose its energy and settle back down. However, if you deliver a series of much smaller pushes and you time those pushes to arrive exactly as the swing begins its backward arc, you can progressively increase the distance it travels. The force of your push did not increase at all, but the organized timing amplified the physical response. That is exactly where the headline movement figure becomes misleading. The 1.5-meter figure tells us the distance of the displacement. It does not by itself tell us whether the movement is becoming organized into a reinforcing pattern, which should actually sound more disturbing to you. One enormous and isolated gust of wind slamming into a facade, or thousands of smaller invisible pushes arriving at the exact right fraction of a second to catch a falling tower and push it further. The environment surrounding Burj Khalifa does not push in a steady and continuous line. Under certain atmospheric conditions, steady wind can actually create its own repeating sideways forces. When an air mass approaches a tall and slender obstruction, the flow cannot simply go straight through it. The wind is forced to separate and travel around the sides of the structure. As this airflow passes the building, it creates distinct areas of low pressure directly behind it. But these low-pressure zones do not form evenly or simultaneously. Instead, a swirling vortex of air will detach from one side of the structure. That detachment creates a localized drop in pressure that briefly pulls the entire building in that direction. A fraction of a second later, another vortex will peel off from the exact opposite side and reverse the aerodynamic pull. This phenomenon is known as vortex shedding. Instead of a continuous wall of blunt force, the wind begins to act exactly like a metronome. It generates alternating aerodynamic forces that pull the building to the left and then to the right in a repeating sequence. What makes this aerodynamic behavior so interesting is that the wind itself is organizing the pressure. It is taking a chaotic and forward-moving air mass and converting it into a repetitive lateral pulse. Wind does not have to behave like a giant hand pushing continuously. But a repeating aerodynamic force only becomes a genuine structural problem when it encounters something highly specific. It only becomes truly dangerous when the structure receiving that pulse also possesses a dynamic behavior of its own. Every physical object on Earth has a natural frequency. It has a specific rate at which it prefers to vibrate when disturbed by an outside force. A structure, as massive as Burj Khalifa, is not a rigid block of solid concrete pinned to the desert floor. It is a highly complex dynamic system, and dynamic systems care deeply about timing. When engineers analyze the dynamic characteristics of this tower, they look at its natural lateral modes. Engineering literature, detailing the structural behavior of Burj Khalifa, reports that its first lateral mode has a period of approximately 11.3 seconds. This means that if the tower is displaced and allowed to oscillate naturally, it takes exactly that duration to complete one primary structural sway cycle. That structural reality fundamentally changes the nature of this investigation. This is where the story stops being only about how strong the wind is blowing across the city. It becomes a highly precise timing problem. If the wind blowing past the tower sheds alternating vortices at random intervals, the building simply absorbs the energy and dampens the movement. But if the wind speed aligns perfectly with the geometry of the tower, those vortices can begin shedding at a rate that matches the internal clock of the building. The alternating aerodynamic pull locks into step with the natural structural sway. The wind pulls right, just as the building is already naturally swinging right. This interaction between an organized aerodynamic force and a natural structural rhythm is what engineers must prevent from running out of control. Yet even an organized oscillation is not exactly the same thing as a structural failure. Something physical has to convert that repetition into localized damage. Take a simple metal strip or a paper clip. If you bend it sharply once, it might hold its current shape without breaking. But if you bend it slightly in one direction, and then return it and bend it in the opposite direction, and repeat that cycle 100 times, the material will snap. The failure did not happen because the final push was stronger than the first. It happened because the repeated stress cycles fundamentally degraded the physical capacity of the material itself. A super-tall skyscraper is vastly more sophisticated than a piece of bent wire. However, the underlying physics of material fatigue remain a rigid engineering boundary. When a tower oscillates in a sustained rhythm, the structural components undergo continuous stress reversals. The steel beams and massive concrete connections are pulled heavily into tension and then immediately compressed. Then they are pulled again. If an aerodynamic force like vortex shedding locks into the natural rhythm of the building, it creates cyclic structural stress. Over time, this repeating demand targets the most vulnerable structural components. This is exactly why the word snap does not mean a skyscraper breaking cleanly in half during one violent storm. It means a progressive local degradation driven by thousands of repeating stress cycles. If a vital connection loses its stiffness or its ultimate load capacity, the forces it was carrying do not simply disappear. They instantly redistribute to neighboring elements. That structural load transfer can easily initiate a much broader sequence of internal damage. A skyscraper does not need to look as if it is breaking for repeated stress to matter deeply inside its structural frame. So far, this timeline of repeated bending and fatigue demand could still sound like an abstract theoretical model. But Burj Khalifa offers something far more valuable to structural engineers. It offers full-scale recorded behavior. The aerodynamic threat was not simply a wind tunnel concern left behind in the design phase. It is a measurable physical reality. A peer-reviewed study published in the American Society of Civil Engineers, Journal of Structural Engineering, documented this exact mechanism. Researchers analyzed structural health monitoring data extracted directly from Burj Khalifa. The highly sensitive monitoring equipment captured continuous accelerations and lateral displacements at extreme altitudes. They isolated the specific dynamic responses recorded between 2010 and 2014. Within that massive dataset, they actively identified vortex-induced vibration responses happening in the real tower. This aerodynamic signature was distinct and significant enough to be extracted and used to evaluate the crosswind fatigue damage of the pinnacle. This discovery requires a very careful interpretation. The monitoring data does not prove that the pinnacle is currently tearing itself apart or that the building is about to fail. Instead, it proves that the very phenomenon engineers fear most, is not just a laboratory simulation. It is an active and verified force acting on the 828-meter structure. The wind actually does organize itself. The vortices actually do shed in repeating sequences, and the structural pinnacle actually does record that dynamic forcing in its physical behavior over time. This is a fundamental shift in the investigation. If the tower possesses its own natural dynamic modes, if the atmospheric wind actively creates repeating aerodynamic forces, and if vortex-induced vibration was undeniably identified in the full-scale data, why did the physical response not simply continue building into a destructive and catastrophic oscillation? The answer to that question begins with the visible shape that most people incorrectly treat as purely decorative architecture. When you look at the exterior of Burj Khalifa, you see a tower that continuously changes its geometry as it rises. The profile steps back in a spiraling pattern. It alters its width and cross-sectional shape at distinct vertical tiers. This changing geometry is not just an aesthetic choice designed to look impressive against the skyline. It is a highly deliberate structural defense mechanism. If the tower were a single uniform cylinder or a massive extruded box, the wind could easily establish a coherent vortex pattern along the entire height of the structure. Those alternating low-pressure zones would organize perfectly and drastically amplify the lateral pull. But because the tower continuously changes its shape, the wind is forced to encounter different physical geometries at different elevations. A vortex attempting to organize coherently at Tier 1 is completely disrupted by the narrower geometry at Tier 2. The structural profile essentially attacks the aerodynamic organization. It prevents the wind forces from sinking up across the vast vertical surface area. What millions of tourists read as a beautiful silhouette can be read structurally as a highly engineered sequence of aerodynamic interruptions. The tower does not defeat the wind by presenting one massive and impenetrable wall. Part of its defense comes from strictly refusing to give the wind the exact same shape repeatedly as it climbs higher into the atmosphere. However, aerodynamic shaping can only reduce and disrupt problematic wind response. It cannot make the immense horizontal pressure disappear entirely. The shape does a significant amount of the work before the force ever reaches the structural frame. But what happens to the massive lateral loads that inevitably remain? Once the wind bypasses the aerodynamic shaping of the exterior, it becomes a pure structural problem. The lateral and torsional demands that the geometry cannot eliminate must be transferred safely through the building and down to the ground. To handle this load, Burj Khalifa relies on a central structural system known as a buttressed core. If you strip away the glass and look inside the floor plan, you will see three massive wings extending outward from a central hexagonal hub. These three wings connect directly through the central structural core. Because of this geometric arrangement, each wing actively participates in buttressing the others against severe horizontal forces. When the wind pushes hard against one side of the tower, the structural loads are absorbed and immediately redistributed through the heavily reinforced connecting walls. This creates an immense amount of lateral and torsional stiffness precisely where a supertall structure needs it most. There are now two entirely different defensive systems working simultaneously. On the outside, the changing shape actively interferes with the aerodynamic organization of the wind. On the inside, the buttressed core manages the physical forces that manage to survive that disruption. This dual approach raises a fascinating question about how we view supertall engineering. If the building alters the behavior of the wind before it ever resists the remaining pressure, is it simply surviving the environment, or is it actively manipulating it? The logic of this combined system makes perfect sense when drawn on an engineering blueprint. But before construction began, no full-sized building of this exact design or extreme height had ever existed in human history. How could the engineering team possibly know that this theoretical strategy would actually work in the real atmosphere? To find dangerous aerodynamic behavior before the massive concrete foundation was ever poured, the engineering team had to build the wind first. They could not simply draw a visually striking silhouette and hope the structure would safely absorb the atmospheric pressure. They relied on specialized testing facilities to simulate the harsh reality of the extreme environment. Engineers placed highly instrumented scale models of the proposed tower into controlled wind tunnels. They subjected the geometry to various wind speeds and directional angles while precisely measuring the pressure distribution across the exterior surfaces. This was an aggressive and highly iterative physical process. The team would test a specific shape and look for any unwanted aerodynamic response, like a coherent vortex organizing along a flat facade. When they identified a problem, they would modify the geometry and then test the new model all over again. More than 40 wind tunnel tests were conducted to thoroughly investigate the wind effects and the dynamic structural behavior of the building. These physical simulations actively guided the orientation of the structural wings and the placement of the setbacks. This reveals a profound shift in how we understand the final design of the structure. The profile of Burj Khalifa was not simply drawn by an architect and then mathematically verified by an engineering team. The wind itself was effectively allowed to edit the building. It shaped the exterior geometry long before the first piece of glass was ever installed. However, a wind tunnel is ultimately a controlled laboratory prediction. It relies entirely on scaled-down dimensions and simulated air currents. But prediction is not exactly the same thing as a full-scale 828-meter structure operating for years in the chaotic atmosphere. What happens if the actual tower behaves differently from the carefully tested laboratory model? The engineering experiment did not actually end when the ribbon was cut and the building officially opened to the public. Opening day merely changed the fundamental process from theoretical prediction to full-scale physical measurement. To ensure the structure performs exactly as the design models expected, Burj Khalifa has been subjected to a continuous structural health monitoring program. Engineers installed a sophisticated network of highly sensitive sensors throughout the building. This system constantly tracks the lateral movements, the overall displacement, and the extreme accelerations happening near the summit. It accurately records the exact dynamic characteristics and the structural response of the tower as it interacts with the weather. This includes monitoring the complex pinnacle dynamic behavior and tracking the ongoing fatigue characteristics of the materials. Earlier in this investigation, we established that researchers could actively identify vortex-induced vibration in the recorded data. But the broader physical purpose of this continuous monitoring system is to test the original engineering assumptions against the brutal reality of the environment. If the building begins to twist or sway in a manner that the wind tunnel models did not predict, this sensory network will immediately capture that deviation. To a structural engineer, the word stable does not necessarily mean perfectly motionless. It can simply mean that the movement remains strictly within a physical boundary that engineers can observe, model, and completely understand. By continuously measuring the dynamic response, the engineering team ensures that the tower is not secretly developing a dangerous aerodynamic rhythm. Which brings this investigation to its final and most disturbing question. If the movement ever escaped those boundaries and became destructive, what would the catastrophic word snap actually mean? A super-tall skyscraper does not need to cleanly break in half like a dry branch for the physical threat behind that word to matter. The real structural failure pathway is much slower and far more insidious than a single violent event. It begins with coherent aerodynamic forcing, successfully organizing around the exterior of the tower. That continuous wind pressure forces the massive structure into a repetitive oscillatory response. The organized swaying creates continuous cyclic structural stress deep inside the steel and concrete connections. Over time, that repetitive stress produces concentrated fatigue demand at the most vulnerable structural components. If that intense fatigue eventually leads to a local loss of stiffness or a severe reduction in load capacity, the structural forces do not simply vanish. They redistribute to the surrounding elements, creating potentially broader and cascading structural consequences. This is exactly why the peer-reviewed study, evaluating the pinnacle, is so vital to understanding the reality of the building. Connecting vortex-induced vibration directly to a fatigue evaluation demonstrates why repetitive wind motion is a legitimate structural engineering issue rather than just a trivial side effect of extreme height. There is no single miracle device protecting Burj Khalifa from this progressive structural pathway. Instead, the building survives through a highly integrated defensive chain. The continuously changing exterior geometry actively disrupts the aerodynamic organization on the outside. The buttressed core aggressively resists the remaining lateral and torsional demands on the inside. The extensive wind tunnel testing revealed the unwanted aerodynamic behavior before a single wall was constructed, and the full-scale monitoring program constantly checks the real structural behavior against the mathematical predictions. When we began this investigation, the idea of a massive structure displacing by approximately 1.5 meters sounded like the ultimate physical danger. But that number was only a doorway into a much deeper engineering reality. The true boundary between structural safety and potential disaster is not the difference between standing still and moving. It is the vast difference between controlled movement and an organized, repetitive, and destructive aerodynamic rhythm. From the street level of Dubai, this towering icon appears completely frozen against the sky. That apparent stillness is a deeply engineered illusion. The survival of the tallest building on Earth does not depend on eliminating every possible movement. It depends entirely on making sure the wind never learns how to use that movement against it. The aerodynamic mechanisms and progressive failure pathways discussed in this documentary are based on publicly available engineering literature and peer-reviewed structural monitoring research. Analyzing these dynamic boundaries is a standard structural engineering practice. This analysis carefully examines theoretical and measured structural responses, and does not claim that Burj Khalifa is currently unsafe or experiencing imminent failure. Would knowing that a super-tall building is intentionally designed to flex and move in the wind make you feel safer at the observation deck, or far more uneasy? Let me know your perspective in the comments below. And to uncover the hidden engineering keeping this city alive, subscribe to the channel.